So in this video, we're going to talk about normal approximations to binomial distributions. Now, for large n, okay, so let me get this spacing fixed up. For large n, it's not practical to use the binomial formula. The CDF formula is the sum from x equals 0 to n of n choose x multiplied by p to the x times q to the x, or n minus x, okay? So it's kind of complicated, to say the least, to do this whenever you're trying to do this by hand or whatever. So there's a way to approximate binomial distributions, and we can approximate them with normal distributions. Now, it only works if n times p is greater than or equal to 5, and means both, n times q is greater than or equal to 5. If these two things are true, then the binomial random variable x is approximately normal with a mean equal to n times p and a standard deviation equal to the square root of npq. Now, n is the number of trials. So maybe we flip a coin 7 times, right? N equals 7. P is the probability of success for a single trial. The probability of success is the same for each trial. Q is the probability of failure of a single trial. Okay? So probability of success, P, probability of failure, Q. Remember, Q is found by doing 1 minus P. It's the complement. There's a 30% chance it's going to rain. That means there's a 70% chance it's not going to rain. Okay? They're the complements of each other. So when we were doing the central limit theorem, and we had just regular data, and it was averages, it was means of sample means, right? We needed n to be greater than or equal to 30, or we needed it to be normally distributed. If I'm going to use the normal to approximate the binomial, my thing that I have to check here is that both NP and NQ, when I multiply those numbers together, I get it to be greater than or equal to 5, okay? That is what I'm checking for this. So before you work your problem, you always check this first, because if this isn't satisfied, it doesn't matter what the rest of the problem says. You can't use the binomial, or you can't use the normal to approximate the binomial. All right, so given a sample size n, a probability of success P, a probability of failure Q for a binomial experiment, determine if you can use a normal distribution to approximate the distribution of x, which is the binomial. So can you use the normal to approximate it? What do you check? You got to check NP and you got to check NQ. Well, here's typically what's going to happen. They're going to give you N, they're going to give you P. And then the question is, well, what's Q? Q is 1 minus P. So this is 1 minus 0.15, which is 0.85. So let's check this out. NP is 20 times 0.15. What does that equal? That equals 3. Well, right off the bat, is 3 greater than or equal to 5? No. Well, if it's not, do I even need to check this? Who cares? Because both NP and NQ have to be true. If one is false and the other one's true, that's still not going to work. And means both. And means both must be true. Okay? So we cannot use, so since n times p is less than 5, you cannot use the normal distribution to approximate the distribution of x. Okay? What about 35? So if p is 20%, q is 1 minus 20%, which is 80%, so 0.8. So NP is going to be 35 times 0.2. And if I multiply that, I get 7. 7 is greater than or equal to 5. I'm okay here. What about NQ? NQ is 35 times 0.8. That is 28, which is definitely bigger than or equal to 5. I'm good here. So you can use a normal distribution to approximate the distribution of x, which is a binomial distribution. So that's how easy it is, okay? That's all you've got to do there. All right, guys, good luck.